I'm going to be talking about coalgebras, coTHH, and traces. And you heard another talk on a related project with Anna Marie Bowman and others. But this is actually a report mainly on joint work with Catherine Hess. And I'll mention other work later on with other groups. OK, so I wanted to start with some examples of coalgebras. So the first example is in the category of spaces with Cartesian product, and the unit is the one-point space. So we have a co-unit from any space X, and we have a co-multiplication. So if we look at the co-multiplication and the co-unital conditions, this shows us that, as we already knew, the co-multiplication has to be the diagonal. OK, so for any space, we have exactly one coalgebra structure, and it happens to also be co-commutative. OK, so that's a very special case, and I'll refer back to that later in the talk. So another example that will appear many times during the talk is if we look at the category of chain complexes over a field K with tensor product, then we can look at, for example, the chains on a space X with coefficients in K. And that's a coalgebra using the Alexander-Whitney map. And of course, it's not necessarily commutative, or not necessarily co-commutative. Another example that we might use is take your favorite differential graded ring and take its vector space dual. Then, with some finite type conditions, we get a coalgebra. OK, and then another setting that will come up today is the category of spectra with the monoidal smash product and the unit, the sphere spectrum. And here, the main example will be the suspension spectrum of a space X with a disjoint base point added. And we have a co-unit to the sphere spectrum, and the suspension of the diagonal gives us a coalgebra co-multiplication. And again, this is going to be co-commutative because it's the suspension spectrum of the first case. Another example that one can actually do in any of these monodal categories is that one could start with a map of commutative rings, and then it follows that B smash over A with B, or I guess smash has become my generic monoidal structure, is, yeah, let me change that. So B tensor over A with B is a B coalgebra. So there have been examples of this that have been mentioned already this week. So for example, in the end of Tyler's talk, he was talking about if you use the map from MU to HC, you get a coalgebra HC smash over MU with HC. And another common example is MU smash over the sphere spectrum with MU. So lots of examples of coalgebras. OK, in the following, we'll need to actually look at co-augmented coalgebras. And in that case, in addition to having a co-unit, I ask that there's a co-augmentation that's a map of coalgebras. So what I need is that epsilon eta is the identity, and that the co-multiplication of eta is eta tensor eta. OK, so these are some of the objects that will appear. I'll be talking about coalgebras mainly in the differential graded setting in the spectral world. So for coalgebra C with co-unit, co-multiplication, co-augmentation, in other words, I want to make sure to say it's a co-augmented coalgebra, then we can define two co-simplicial objects. So one of these is going to be coTHH that you've seen in Anna Marie's talk, and which is dual to Hochschild homology. And the other will be the cobar complex. But let me first start with coTHH. So the co-Hochschild complex in the nth cosimplicial level, I'm going to take the tensor product of our coalgebra C n plus 1 times. And this is going to use what's called also the cyclic cobar construction. So the co-face maps are given by taking the co-multiplication in the ith spot. And the co-face maps are given by taking the co-unit in the ith spot. OK, but then there's this twist that we have to do. So the last co-face uses a twist. So the last co-face, if I take the co-multiplication, then I take the last piece and twist it around to the first. OK, so that makes it the cyclic cobar construction. And then stepping back, we could also define the cobar complex. So here, for a co-augmented coalgebra, I take C tensor to the n in the nth degree. And then it's useful to think of this as the unit tensor C to the n tensor the unit, so that it makes sense for me to say that the face maps use either the co-augmentation in the 0th or the last spot, and the co-multiplication in the ith spot. And again, the codegeneracies use the co-unit in the ith place. OK, so hopefully this is familiar from previous talks this week. And the cobar complex, I'm just having one less copy of C in each level. And then I do not have any twist here. OK, so those are the cosimplicial objects that will appear in this talk. And in the general approach that I've been sort of talking about so far, I'm thinking about a generic monoidal category. I now want to move into some homotopy theory and have a way to totalize. So totalizations here, for the general approach, as we saw in Anna Marie Bowman's talk, we want to define coTHH of C as an object back in our underlying category as the homotopy inverse limit in that category of this cosimplicial object. And similarly, and I'm going to decorate this. So similarly, the cobar construction, in general, I would want to define this to be the homotopy inverse limit of the cosimplicial object given over here. So it turns out homotopy inverse limits are difficult. I've been working on them since my thesis. To do calculations here, often you need one connectivity or other similar hypotheses so that you have convergence in the right places. So often when I'm referring to these things, I'm going to be using connectivity conditions. But in the differential graded setting, what I want to do is actually just give a simpler definition of what I'm going to do for totalization. So instead of taking the homotopy inverse limit, which may involve infinite products, I'm going to instead give a definition that's based on infinite direct sums. So in the differential graded case, well, first let me say, so from now on, I'm going to be looking at coalgebras over a field K, which are zero connected. So zero connected, co-augmented, differential graded K coalgebras is the setting that I'm going to always be working in for K a field. So here, I actually want to take the usual definition and take the cobar complex to be defined as, well, I first take, sorry, let me write this all down. I first take the co-kernel of eta, the co-augmentation, and call that C bar. Then I'm going to shift it down 1, and then take the tensor algebra on this. Okay, so then my differential is given as a combination of the internal differential that we still have on C bar and the tensor algebra differential that actually is still coming from this co-simplicial object. So let me just point out that if C is 1 connected, then this cobar construction that I've defined right here is quasi-isomorphic to the cobar construction that I defined over here. Okay, so that gets rid of the infinite product versus infinite direct sum worries. But I'm not always going to be looking at 1 connected coalgebras, and when I'm not, I mean this definition. Okay, and it's the standard differential grade. If you're an algebraist, this is the only definition you know, because you don't know about homotopy limits, right? So another reason to talk about the cobar construction, just to give an idea for us, since most of us are topologists, if we have a space X which is 1 connected, then this cobar construction does what you might have thought, given that I'm using the symbol omega. The cobar construction on chains on a space X is quasi-isomorphic to chains on the loop space X. So there's the reason for omega. OK, then similarly, I'm going to define co-Hauschild homology of coalgebra C to be, again, based on this direct sum version, where I need to tensor in an extra C, just like I do for the cobar complex and the cyclic cobar complex. So I'm adding in a copy of C, and again, the differential is given by combining the internal differential and the differential that comes from the Hauschild complex. Okay, so again, this is the usual definition of co-Hauschild homology. Okay, so that was a lot of definitions. Hopefully some examples to keep you awake on a Friday afternoon. Okay, so next what I want to do is develop some of the properties of co-Hauschild homology in the differential graded setting. And some of these properties are going to be similar to the properties that the Hauschild homology has for differential graded algebras. So the co-Hauschild homology has been considered by various authors before, and one of the reasons that it was studied by some of the people we know, so Hess, Pratt, and Scott in 2009, were studying co-Hauschild homology because they wanted to have a model for the free loop space. That was one of the motivations. So they show that for X1 connected, the co-Hauschild homology on the chains on X is quasi-isomorphic to the chains on the free loop space. And then in further work, Hess showed that the another identification of the co-Hochschild homology for any coalgebra C can be given in terms of Hochschild homology. And here I need C connected. So the co-Hochschild homology on a coalgebra is actually quasi-isomorphic to the Hochschild homology on the co-bar construction on C. So when you see this, you might say, OK, so why did we need to define this side of the equation? Well, C is a smaller object than the co-bar on C, right? So the hope is that there are going to be times when the co-Hochschild homology of C is going to be simpler and smaller to calculate than the Hochschild homology on a large complex on C. OK. Another thing that was noticed here is that if you take the co-Hochschild homology and take the vector space dual, then that is actually isomorphic to the Hochschild homology of the DGA given by the vector space dual. OK. So these were very useful results to understand co-Hochschild homology, but we might ask, where are they coming from? So is there an underlying reason why co-Hochschild homology agrees with Hochschild homology of the co-bar construction? And I'd like to suggest that the reason is the following result. So in ongoing work, Hess and I have shown that for C connected in this category of co-augmented differential graded K coalgebras over a field, then there's actually a Quillen equivalence underlying this equivalence, which says that if you look at the category of comodules over a coalgebra C, then that is Quillen equivalent to the category of modules over the cobar on C. So I've been using it implicitly here, but I should have pointed it out. Since I'm taking a tensor algebra here, my cobar construction does give me an algebra, right? So it makes sense to be talking about the Hochschild homology and to be talking about modules. I skipped over that. OK, so a little bit of background on this theorem. So in order to talk about a Quillen equivalence, I first need to give you a model structure on both sides to actually define a model structure, a homotopy theory for these settings. So first of all, on Z-graded chain complexes over a field, there's a standard model structure with cofibrations, the degree-wise injections, fibrations, the degree-wise surjections, and weak equivalences, the quasi-isomorphisms. So then there's a standard sort of lifting for any differential graded algebra where we can take the free module on a chain complex, we get a module, or we can forget. And then we define the model structure on modules via the underlying functor for weak equivalences and fibrations. Okay, so for modules, the underlying fibrations and weak equivalences are used. And then the cofibrations are built by tensoring with the free ring. OK. The key to this result is actually being able to define a model structure on comodules over this coalgebra C. Catherine and I have been working to construct such a homotopy theory for quite a while, and it turns out to be quite nice. So just like we can do a right lifting for modules, we can actually do a left lifting for comodules. So if you have a comodule, you can forget down to a chain complex, and that has a right adjoint given by taking the co-free comodule, given by tensoring with C. And here we can use work with Catherine and I and Magdalena Kedzorek and Emily Riel. So to show that there is a dual of the usual Quillen path-object argument, which holds often when you have a category of all objects being fibrant. So here we're going to have all objects being cofibrant and use the chain level interval. And it turns out that one can just keep going if one knows enough category theory. So here we're going to define the underlying cofibrations and quasi-isomorphisms. And fibrations, so if we take a surjection and tensor with C, then we get a fibration, and we can pull back and construct fibrations in the comodule category. Okay, so that really is the key to this Quillen equivalence, that we first had to define a homotopy theory for comodules. But then let me fill in just a little bit more for something that's going to come up in a minute. So I should tell you what the functors are. So functors going back and forth, and the right adjoint is tensoring over omega c with object I'm going to call P. So P is a based path space model. So there's a twisting that one can form between the cobar on C and C to construct analog of a based path space. And going the other way, we cotensor over C with a similar based path space. Okay, and then I should have left room on this board, so I wanted to point out that if I start with the object omega c here, then if I tensor down over omega c with P, P is a contractible object, and so this omega c is taken to the comodule K, which is given by the co-augmentation. And, it's weakly equivalent to K. And similarly, if I start here with my, I guess, why not use a different color? If I start with my Coalgebra C, then that, again, is taken to object that's weakly equivalent to the field as a module over omega c. Okay, so it's, I haven't said why this is Quillen equivalence, but that is relatively simple compared to setting up the homotopy theory. So you can check that the composites in both directions are weakly equivalent to the identity. Okay, so the fact that these homotopy theories agree that comodules over the coalgebra C and modules over the cobar on C agree is really what is telling us that we have a quasi-isomorphism here. Okay? And this also gives us several other properties that we would like to know about coaxial homology. So one of those statements is about agreement. So this property says that if I look at coaxial homology on a coalgebra C, then that's going to be quasi-isomorphic to what I would get if I took the Hochschild homology on the differential graded category defined by comodules over my coalgebra C. So I'm in the differential graded world. I didn't emphasize it, but there's a enrichment for comodules. I can talk about the mapping objects. Those are underlying chain complexes. And so therefore, I have a differential graded category, which I can think of as a differential graded algebra with many objects, and therefore have a very similar definition to the usual Hochschild homology, and define Hochschild homology on a differential graded category. And we can see that this is actually going to be quasi-isomorphic to our definition of co-Hochschild homology. So just the sketch here is that we can use this result from Hess to identify coaxial homology as quasi-isomorphic to axial homology. On the Coalgebra construction, we can then use agreement for the differential graded algebra case and see that this is the same as the axial homology for modules over the Coalgebra construction. And then we can, knowing that we have a equivalent equivalence here, then that implies that the equivalent equivalence will be associated to a quasi-equivalence of differentially graded categories and thus induce a quasi-isomorphism on the axial homology. OK. I guess I should have mentioned a few names here. The development of axial homology for a differential graded category was based on work of McCarthy for exact categories and then developed further by Keller and Tabawada. OK. One other property that you might want to know about coaxial homology is Morita theory, Morita equivalence. So in this setting of comodules, one actually talks about Morita Takeuchi equivalences. And in the interest of time, I'm actually not going to say much here. So there's a paper by Alexander Berglund and Catherine Hess, which considers Morita equivalences in a very general setting. And the Morita equivalences here follow from their work. So there's a little bit of technicality here. So one does have some hypotheses. So I shouldn't. The Morita equivalence, at least so far, we don't have as general a result as one would want for to have the generality that the axial homology side has. OK. Good time for a pause. So then finally, I wanted to talk about connections to K-theory, so the traces part of my title. So that's one of the reasons that we are always talking about axial homology, topological axial homology, is because we have a trace from K-theory. And so that was another motivation for developing coaxial homology. We want to have traces from K-theory to coaxial homology. So first, let me make some definitions. So I'm going to be talking about thick subcategories of comodules. So for example, I might say that I was looking at the thick subcategory of comodules over C generated by some object G. And then another setting that I'll be talking about thick subcategories is if I look at the thick subcategory of modules over the Coalgebra construction generated by an object G. So these are going to be subcategories of the homotopy category, which is a triangulated category. And thick subcategories are closed under triangles, closed under extensions, cokernels, kernels. OK. So following Waldhausen, we can define a Waldhausen subcategory of a model category to be all objects such that they are isomorphic to one of the objects in the thick subcategory in the homotopy category. So I'm going to define the K-theory of a coalgebra C to be the A theory, or in other words, the K-theory due to Waldhausen, based on the thick subcategory generated by the field as a comodule over the coalgebra C. So the reason I'm doing this is because this thick subcategory actually corresponds to the category of compact objects in the category of comodules. Okay? And then we'll also define the G theory of C, and that's given by the A theory of the thick subcategory generated by C. Okay, so these are analogs of the case where if I look at the cobar construction on C, or in other words, I have an algebra, then there the K theory is defined to be the A theory, or it's equivalent to the A theory, the Waldhausen K theory, associated to the thick subcategory of modules of the cobar construction generated by the free ring itself. So for modules, the ring generates the compact objects. And so that's why we take the thick subcategory here. And the difference here is that the compact objects are generated by K. OK, and then similarly, the Swan K theory, G of omega C, is defined to be the A theory of the thick subcategory of modules over the cobar of C generated by the field. OK, so now we notice that this Quillen equivalence is going to induce equivalence on the triangulated category level of the homotopy categories. And therefore, it's going to induce an equivalence between the thick subcategories. So here, if I take the thick subcategory generated by the field, it's going to be identified with the thick subcategory generated by the ring, omega C. And similarly, the thick subcategory generated by the object K as a module is going to agree with the thick subcategory generated by C. So the corollary is that the K theory of the coalgebra C is equivalent to the K theory of the cobar on C, right? Since K is taken to omega C and vice versa. And imagine that, we used K for both of those, right? OK, and then, as you might guess, the G theory on a coalgebra C is identified with, the G theory on the cobar on C. So again, that's because the object C, the coalgebra as a co-free comodule, is taken to the module K. OK, so given these identifications, we then get trace maps via using the standard trace maps. So this isn't, of course, as exciting as it would be for me to define a trace map just in terms of coalgebras. And that is our hope. But for now, let me tell you what we can get. So for C connected, we use this equivalence from the K theory of the coalgebra. We move to a K theory of an algebra, take the Dennis trace to the Hochschild homology of that algebra. And then the identification that I just erased is that the Hochschild homology on the cobar construction is quasi-isomorphic to the co-Hochschild homology on C. And therefore, we get our trace map from the K theory of a coalgebra to the co-Hochschild homology of the coalgebra. So we can also get a trace map in the G theory. So another result that I just erased, well, let me say something here. So here I want to use the functor that goes from comodules over the coalgebra C to modules over the dual of the coalgebra. That gives me a differential graded algebra. And so I notice that the object C is taken to the dual C, the dual of C. And so the G theory of C was generated, was associated to the thick subcategory generated by C. That's taken to the thick subcategory generated by the dual, and therefore we get a map to the K theory of the dual. Then again, applying the classical Dennis trace, we get a map to the Hochschild homology of the dual, and that is isomorphic to the dual of the co-Hochschild homology. So again, we get a resulting trace map. Okay. Okay, so that's some of the properties that we know about co-Hochschild homology for the differential graded world. And now I want to move to the world of spectra. So maybe I'll pause for a second in case anyone has any questions about the differential graded world. Yes, Randy?
If you use the color model for Hochschild homology on the chains, so you could have gone directly from KSC to the Hochschild homology of the fixed subcategory, does that give you the same variance that you're seeing for this composition?
So sorry, if I had gone from the K theory of C to the Hochschild homology on cobar of C?
Fixed subcategory, I mean, that's what we count out and work directly with the category, right?
Yeah?
So I mean, there's an ordinary Dennis trace map from KSC to the Hochschild homology of that fixed subcategory.
Yeah,
And
right.
if you use Heller's chain complex model, does that recover this same variance?
I would expect so. I guess that would come from checking that. Yeah, I'd have to think about it, but I would expect that.
Yeah, it's just
basically,
that equivalence in one of the categories.
Right. Right.
Corresponding with the Hochschild.
Right. There's no way that something else could be happening.
I didn't think so.
Yeah. Anything else? Okay. So let's talk about spectra. So I want to look at any of our new, well, not so new, any of our good categories of monoidal categories of spectra. So this is any of our monoidal model categories of spectra. So in particular, any of the diagram categories like symmetric spectra, orthogonal spectra, or also the S modules of Elmendorf, Kreis, Mandel, and May, or gamma spaces, or W spaces, or simplicial functors, or, okay. So any of those nice categories of spectra, well, as I mentioned at the beginning, the suspension spectrum of a space with a disjoint base point is an S coalgebra. There's a co-unit, a map to the sphere spectrum, and there's also a suspension spectrum of the diagonal, and that's going to be, in fact, a co-commutative. S coalgebra. So this is a nice commutative S coalgebra in any of these settings. And it turns out that it's basically the only example of an S coalgebra. So based on an observation with Catherine, my student Maximilian and Peru and I showed that in any of these good categories of spectra, they will all be co-commutative. So let me write this down. So any S coalgebra in one of these categories is co-commutative. And maybe as a little further view into this, for any S coalgebra C, one has a set theoretic surjection from the sphere spectrum smash the zeroth space to C. So sorry, that is surjective. So the sketch of the proof that I'll give is that it follows from the case of spaces. So it follows as for spaces. So at the very beginning, I mentioned that for a space, I'm pointing to where it was, if you look at the commutable properties, that forces the co-multiplication to be the diagonal. And that's basically what happens here. On the suspension spectrum of the zero space, there will be only one Coalgebra co-multiplication structure, and it will be forced to be the diagonal. And then since that surjects onto C, that will force the co-multiplication on C to be co-commutative. So what am I saying here? I'm saying that all my favorite categories of spectra do a really good job of modeling algebras modules, but they don't model coalgebras as we know them. So just for those of you who also love these categories, let me mention that they're built to so that the homotopy invariants agree with the invariants. Sorry, co-invariants. The one time not to say, okay, let me add a co to that sentence. These are built so that the homotopy co-invariants agree with the co-invariants. And that's why, for example, the commutative rings in these categories agree with the E-infinity rings. But they don't have the same property for the invariants. So that can be seen looking at these as coalgebras. So it would be great if someone wanted to come up with a new category of spectra that modeled coalgebras. Well, lots of you here know what that is. You're like, yeah, you're just old-fashioned. So yes, of course, we can use an infinity category of coalgebras. And that is work that is ongoing with Bowman, Gerhardt, and Ziegenhagen. So we don't have results yet on that in that setting. So instead, I'm going to stick with the suspension spectra and talk a little bit about what happens when I look at the suspension spectrum as a coalgebra spectrum. Yes?
Do you have any example of a coalgebra is not a suspension spectrum?
Well, so notice what I said is, so for these models, no, because, well, maybe we can fool around and see something that's slightly not a suspension spectrum. But so for infinity category of spectra, then you would expect that if you have any, even a strict ring spectrum, a finite or compact ring spectrum, the Spanier-Whitehead dual, you would expect to be coalgebra over the sphere spectrum, for example. Okay, so that's, and of course, then you can take a non-commutative ring, and that would give you a non-co-commutative S coalgebra. Right. One can look at this, for example, also over the Einenberg-MacLane spectrum HC, and then one also has some examples. Okay. Okay, so for now, I want to look at the coalgebra given by the suspension spectrum of X. There is a glare. Okay, I have a few minutes. Okay, so first I want to mention that when X is one connected, then the Kobar construction on the suspension spectrum of X gives us the suspension spectrum on loops X. And if we look at the coTHH of the suspension spectrum, then that agrees with the suspension spectrum of the free loop space. So Kary Malkovich writes down the second statement, although he doesn't name coTHH. But another way to prove both of these results is looking at the convergence of the Eilenberg-Moore spectral sequence. And that's basically why one needs the one connectivity here. OK, so with that in mind, hopefully it's not a surprise that one can show, and this was actually work that was done earlier by Hess and myself, that comodules over the suspension spectrum of a space X is equivalent to modules over the suspension spectrum of the loop space. So this is the analog of this result, right? And here, the Coulomb equivalence holds as long as X is 0 connected. OK. So we also have to develop a homotopy theory of comodules, and there are two approaches. One can use the HKRS machine, the left lifting machine, to get a structure here. What we also do is look at an unstable model structure on comodules over a space and stabilize. So the structure that we're actually using here is the stabilization. So as with the functor over there, this functor, let me just write this direction, is smashing over the suspension spectrum with the based path space. So that may have a just right base point. OK. So what we can see is that, as in that case, the suspension spectrum of the loop space is taken to a trivial, weakly trivial object, the sphere spectrum. OK, I don't know. Maybe that's not trivial. It's the analog. Sorry, it's the unit. There we go. It's the analog of the field K. OK. And also, you can see that the suspension spectrum here is taken to the sphere on the other side. So we get the similar results to these. Yeah. So it's time for me to do the bad thing and just fill in what should be here. So as a corollary, for x connected, one gets the result that one would have expected here. And we put some t's. So we can get, again, a trace map. Here, I need to take my space to be one connected in order for both of these objects to agree with the suspension spectrum of the free loop space. Okay? So the trace map exists, and lands here for x, a one connected space. And what we would hope is that, in fact, there is a trace map in the zero connected case. And that's something that's ongoing work. OK, and then one can similarly take the duals here. No, OK, it's the last minute of the conference. Let me not do it. So the same results here works where you take the Spanier-Whitehead dual and take the Spanier-Whitehead dual on the outside here. OK, thanks. Tyler.
So when you were doing the DG context, you have this version of the totalization direct sum. Is there any hope that there's like a homological that might translate into something like Coalgebras, like a cobar?
So sorry, you're saying, so with the differential graded context, I gave a different definition rather than using the homotopy inverse limit. And then you ask for the space for the spectra version. Do I have a similar thing to do? So I have thoughts about that, but maybe not on a microphone. They're not great thoughts. They're some cloudy thoughts that I could talk about. Yes.
So if you work over a different base coalgebra, then there are some interesting ones.
So we have some results over some different bases. In fact, the main thing that we need here is that the zeroth space is S naught. And Maximilian might be able to tell you more about that if you'd like to talk to him. Yes, Randy.
I mean that there's no coalgebras that has negative homotopy groups, or is there an assumption?
No, sorry. OK, let me not leave this on the board, right? OK, so any S coalgebra in these categories is like this. OK, but this is not the homotopy theory, homotopy theory of S coalgebras. OK, these are bad categories for coalgebras. OK, so no, I think that there are S coalgebras for example, the Spanier-Whitehead dual of connective algebra. Right, right. Yes?
Suspended spectra and loop spaces or infinite loop spaces show up in top Galois extensions. What does coTHH measure of these
Right.
algebras?
Right. So that was the very original, one of the other very original motivations for studying all of this. And I don't have much to say yet. So I think we need to have this, infinity category model to be able to really say something more about that.